Hi everyone, and welcome to our first lecture on forest hydrology. Our learning objective for Part 1 is to identify and explain the characteristics that make forest hydrology unique from other ecosystems. The first thing that makes forests unique is that they are continually under change, whether it is from commercial forest harvest, land clearing for agriculture, or forest fire. This graph shows annual deforestation in the Brazilian Amazon since the late 1990s. Increased environmental regulation slowed forest loss in the early 2000s, but there has been an uptick again in the last 2 years that reflects Brazilian President Bolsonaro's push to open the Amazon to more logging, large-scale mining, and industrial agriculture. The numbers for 2019 do not reflect forest loss due to the large-scale fires last year. Deforestation also occurs in the U.S. and can be seen most dramatically in the mountains of the Pacific Northwest. These two images show commercial tree farms in western Washington and British Columbia, Canada in the 1990s. These slopes were previously covered with mature Douglas fir trees that were clear-cut harvested. On the previous slide, I referred to the slopes as experiencing clear-cut harvesting. Clear-cutting is the practice of removing all of the trees and understory at one time, so that the area can be prepared for uniform new planting. It is a very efficient method of timber removal. In contrast, a shelter wood cut selectively removes a portion of the mature trees in order to open up the forest, but some sheltering trees and understory remain, preserving wildlife habitat and other ecosystem services. This picture shows a shelter wood cut from Yellowwood State Forest in Indiana a few years after the cut took place. I was part of a group of Purdue professors who were working with the state forest and a citizens' watershed management group that were concerned about the state's management of the forest land. Despite the dramatic pictures of clear-cut harvest along the Pacific coast, historically the largest forested areas in the U.S. are in the north and southeast of the country, as shown in the inset figure to the right. This land experienced a dramatic decrease in forest area throughout the 1800s up until the Dust Bowl and Great Depression in the 1920s and 30s. Much of this land clearing was for agriculture, and to some extent for fuel and building materials during the Industrial Revolution. Forested land area in the east increased, a process called afforestation, during the 1900s as marginal agricultural land was abandoned, but continues to go through cycles of decrease associated with urbanization in modern day. Another big driver of forest change is forest fires. The graph on the right shows both the number of forest fires and the acreage burned in the U.S. over the last 3 decades. Although the number of fires per year went through a period of decline in the 2000s, the number of acres burned has increased during this period. This likely reflects both forest management practices and the influence of climate change. Management practices that suppress forest fire allow excessive fuel supplies of dead trees to build up. When a fire does occur, it therefore burns hotter and longer and can be more difficult to treat. Decreases in precipitation and shifts in the annual monsoon winds associated with climate change can also exacerbate this situation by leading to excessively dry conditions and increased disease pressure on forests. The second thing that sets forests apart is the way water cycles through them. Forests only exist in areas with abundant annual precipitation. Forest soils are highly conductive, encouraging infiltration of precipitation into the soil, while mature trees can transpire at an incredible rate, returning that water back to the atmosphere. Because of the constant source of organic matter input to the soil through decaying leaves and other plant materials, as well as the dense network of roots, undisturbed forest soils typically have an O horizon, or duff layer, composed of fine roots and decaying organic matter. This not only provides a rich habitat for all kinds of creepy crawly things, but it protects the surface of the underlying mineral soil and leads to very high infiltration capacities in forest environments. As a result, overland flow is rare in undisturbed forest environments. Walking through the woods during a rain event, you will not see water flowing over the soil, except maybe along your compacted path. These pictures show the results of a field experiment in which the researchers used dye tracers to see the path of water through the soil cross-section. The water was traveling rapidly downslope through cracks and macropores in the soil. This means that rather than overland flow, rates of inner flow tend to be very high in forest environments. Forests often exist on steep slopes. One, because forests need high rates of precipitation, and there's more precipitation in the mountains, and two, because flat forest lands are cleared for agriculture first. The steep slope, coupled with high infiltration capacity and a highly conductive surface horizon, means that water moves downslope through the macropores or along the O horizon, A horizon boundary. And of course, transpiration rates are very high in a forest environment. According to the U.S. Forest Service, a 100-foot tall tree has about 200,000 leaves and can transpire over 11,000 gallons of water in one growing season. The last thing that sets forests apart is their ability to intercept precipitation and hold it in the canopy. This slows down rain velocity and further protects forest soils from the potential for erosion and overland flow. In addition, that intercepted rain is more exposed to the atmosphere and so is more likely to evaporate than reach the land surface. This illustration shows the ratio of interception losses to annual precipitation versus annual precipitation for studies across the United Kingdom. You can see where this curve flattens out, that in this climate, across multiple studies, about 30% of precipitation is lost to interception. That means that the effective precipitation reaching the forest floor is 30% less. Things can get even more interesting in environments where a substantial portion of the annual precipitation falls as snow. Trees can potentially hold even more snow than rain because snow can balance on the leaves and stems more. Because the temperature conditions influence snowfall and texture, studies show that climate is more important than tree shape in determining how much snow is intercepted, but it can be substantial. Up to 60% of the annual snowfall can be intercepted by the tree canopy, and if that snow evaporates, that is 60% less snow reaching the ground. The graph on the right shows the results of a field experiment conducted in western Oregon in which 3 trees were weighed all winter, and the change in mass was used to determine the time series of snow interception in the canopy. How do you weigh a tree, you ask? Well, it isn't easy. In this case, the trees were cut down just after things got cold in the fall, and a load cell, essentially a scale, was installed on the tree stump, and the tree was put back into place and held up all winter. Since conditions were below freezing, the tree didn't really know it was dying until the next spring. This concludes part 1 of our forest hydrology unit. You can continue with part 2, where we discuss what happens when you cut all the trees down.